So for my Chapter 2 problem, I chose to do number 51, which states that a test rocket is fired vertically upward from a well. A catapult gives it initial speed of 80 meters per second at ground level. Its engines then fire and it accelerates upward at 4 meters per second until it reaches an altitude of 1,000 meters. At that point, its engines fail and the rocket goes into freefall, with an acceleration of negative 9.8 meters per second squared. And the questions are: A. For what time interval is the rocket in motion above the ground? What is its maximum altitude? And what is its velocity just before it collides with the Earth? Okay, so this is my really nifty artistic diagram. So as you can see, the rocket is going up from the ground at a speed of 80 meters per second when it gets to this spot, and then it goes to a height of 1,000 meters with the engine running. And then the engine turns off, but it still has momentum, so it continues up to the top, and then it eventually falls all the way back to the Earth. And we set positive going up. So in order to solve this problem, I'm going to divide it into three parts. The part that's with the engine on the way up, without the engine on the way up, and then back on the way down. So using these three different portions of the flight, I'm going to be able to determine various questions that the book asked. So the first thing is, with the engine on the way up, the three things that we know are the initial velocity, which it says is 80 meters per second when it gets to the level of the ground, and the acceleration. It says that it accelerates at a constant speed of 4.0 meters per second squared as the engine is thrusting up. We also know that the total change in x of this portion is 1,000 meters because the engine shuts off once it gets to 1,000 meters. So using this information, I chose this equation, which is velocity final squared is equal to velocity initial squared plus 2a change in x, because I had three different variables of this equation, and I was able to solve for the velocity final. And the reason I wanted to solve for the velocity final is because I wanted to be able to solve for what was happening after the engine shut off. And if I had the final velocity, I would be able to determine how high the rocket actually went at that point. So once I had the velocity final, I could figure out some other information, such as the time, because the first question it asks is, for what time interval is the rocket in motion above the ground? So if I wanted to figure out the time interval, I'd have to figure out the time interval in part 1, in part 2, and then eventually in part 3. So I figured out the time interval using the equation velocity final is equal to velocity initial plus acceleration times change in time. And I plugged in my knowns, and then I solved for the change in time, which is 10 seconds. So that's on the way up. Now, secondly, we're going to look at what happens after the engine shuts off on the way up. So this is at this point in the diagram when it's 1,000 meters in the air, and it's still moving upwards just with no acceleration coming from the engine. So we know from this problem up here, the velocity final of the portion with the engine is going to be our velocity initial for this portion. So we know that at this spot, 1,000 meters, it's going to be traveling 120 meters per second. The velocity final is going to be 0 meters per second. Because if you think about it, when this rocket reaches the absolute apex of its flight, it's not going up anymore. So its velocity is going to be 0 meters per second in that direction. It's completely stopped and it'll be turning around in a second. The other piece of information that we know is the acceleration, because we know that the constant acceleration is always going to be towards the Earth at 9.8 meters per second squared. And as you can see, we define positive as upwards, so the acceleration is going to be in a negative direction at negative 9.8. So as you can see, in this portion, I also have three of the variables defined for me, so I can also solve for the two missing variables that I don't have. So I use the equation velocity final is velocity initial plus acceleration times change in time, because I wanted to solve for the change in time to add to my change in time up here, so I could help get to the total time. And so once I solved for the change in time, I also wanted to solve for the change in x, because in order to figure out question B, which is what is its maximum altitude, I would need to figure out how far up it went from here to reach its apex. So in order to do that, I use the equation change in x is velocity initial t plus 1/2 acceleration t squared, since now I did have that change in t number from above. And I plugged everything in, and I got the change in x was 734.7 meters. So now we know, combined with this information up here, that the rocket reached a total apex of 1,734.7 meters. So this leads us to our final section of the rocket's flight, on the way down. So in this section, there is no acceleration provided by the engine. It's all in free fall. So if it's in free fall, as we just said, the height will be 1,734.7 meters above the ground. We know that the initial velocity is 0 meters per second, just as the same as we said before. As you can see, the velocity final of the previous section is going to be the velocity initial of the next section going down. So because it's at the top and it's going into free fall, initially it has no velocity whatsoever. And we know, same as above, that the acceleration is going to be a constant negative 9.8 meters per second squared down towards the Earth if there is no acceleration coming from the engine. So as you can see, conveniently, once again, I have three variables that I can use to solve for. I use the velocity final squared is equal to velocity initial squared plus 2 acceleration change in x for this because I wanted to find the velocity final because that's what we need for part C. Part C asks, what is its velocity just before it collides with the Earth? So as you can see, you need a lot of different pieces of information to solve this problem. So once I had the velocity final, I could use arguably the easiest equation, which is velocity final is equal to velocity initial plus a change in time. And once I had this, I could solve for the change in time in the final section, which could help me as I added up 18.8 seconds, 12.24 seconds, and 10 seconds in order to get a total time of 41.04 seconds. So this answers question A. For what time interval is the rocket in motion above the ground? Question B asks for the max altitude. Well, we already figured that out as we knew that it went 1,000 meters with the rocket and 734.7 meters without the rocket. So, as we used on number 3, the max altitude was 1,734 meters, roughly. And now, as we solved in the final section, question C asks what the final velocity is when it hits the ground. And here we can see that the velocity final is going to be negative 184.4 meters per second. And keep track of the negative. The negative, remember, we assigned positive is going to be up. So the rocket's going to be coming down as it's hitting the ground. So its velocity is going to be negative in relation to our positive axis that we set. And because we solved it up here using these variables in this equation, our velocity final is negative 184.4 meters per second. So that solves A, B, and C of this somewhat long problem, but it's pretty straightforward if you plug in the variables that you're given and then continue to use them as you look at the various portions of the rocket's flight. Hope that helped.